Welcome back everyone, it's Berat again. Let's continue with how do we implement this Oracle function. Okay, now what we want our Oracle function to do is actually take this x0 state, okay, and map it to xfx state. Now f is something that we're going to define, but in order to do this mapping, let's do something, let's do it step by step. Okay, in the first step, what we want to do is we map, we copy this x bit strings to the second register. We can do this easily by applying a lot of CNOTs, like CNOT between each corresponding qubits, and you will have copied this state. Okay. Then after making this copy, now what kind of an fx do we want? Okay, we want this fx, okay, to be in such a way that, for example, you're going to map this x state into some fx value, but there's also be another value, y, that will also be mapped to the same fx value, where y is equal to x XOR s, right? So what happens if we map half of the inputs, okay, to itself, and exactly the other half of the inputs to the XORed versions of themselves? All right, that's like the key idea here. You map half of the inputs to themselves, do nothing to them, and the other half of the inputs you map them to the XORed versions of themselves. Now, just to not make the function so trivial, we apply x gates to the end, but you will see that it doesn't do much. Like at this point, actually, you're done. Okay, let me go over an example, like a specific example, so that it makes everything more clear for you. Okay, let's say our system is a 3-qubit system. Like actually, it's like 6-qubit, like the bit string, like this is 3, amazing. And our secret string is 101. Okay. Now I need to choose half, like exactly half of the states to be mapped to itself, and exactly the other half of itself to be mapped to XORed versions of themselves. Okay. Now, in order to choose like this this choice, to make this choice, you can just actually take an index, okay? And for each index, if this, say, is 0, this index is 0, you map it to itself. If this index is 1, you map it to XORed version of itself, all right? Now, but we need an algorithm to do so, right? We're going to write some code. So let's choose this index that we're talking about. I'm going to call it I, this ith index, to be the rightmost index of S, okay? In this case, this is the, let's say, third index, all right? For example, if this was 110, it would be the second index. Anyways, so for each bit string, like, although I've written it here as a table, this is like a quantum state, okay? That's what we want to do. We want to map 000 to 000, like do nothing to it, because it's this index, third index, is the same. Yeah, it's 0. Now for 001, however, we want to map it to XORed version of itself, like the second register. Now if you XOR 101 with 001, you obtain 100, right? Again with 010, you do nothing, and for 011, you map it the second register to XORed version. Right. Once you do this for all the states, what you have is this state. Now let's have a look at this like quantum state, and note that this is a superposition. Now for each S and Fx state, like for each X state, we have this like Fx, okay? And this Fx is also exists for another state, for example in here, and this is a Y, right? X Fx, Y Fx. Remember the definition that we have given here. This Fx will be like observed for two different states, right? X and Y, where Y is X XOR S, right? Let's now have a look if this actually works or not. Now, if you XOR 101 with 000, what do you get? 101. Yay! That's exactly what we want to do, right? For 1000, for example, if you map XOR 001 with 101, what do you obtain? 1 0 0, right? We kind of like did some sort of a trick. We knew, okay, we knew that this fx value will going to be same for x and y, where y is x XOR s, okay. Now instead of like calculating this fx, or instead of saying, okay, let me map 0 0 0 to like 1 1 1, what we did was just choose half of them, okay, and map half of them to themselves and the other half to XOR versions of themselves, because these like themselves think like if x is equal to y XOR, you're gonna get it from some other index, in this case for example 101, for which y is equal to x XOR s. Okay, it's a little bit tricky, but if you just like work it around, you will understand it. Now, just not to make our Oracle function so trivial, we just apply some X gates to all the qubits in the second register. So you just like bit flip them 0 0 0 to 1 1 1, etc. to do the mapping. So in the end, our function maps 0 0 0 to 1 1 1, okay, 0 0 1 to 0 1 1, and it also maps 1 0 1 to 1 1 1, which is x XOR s. Like 1 0 1 is equal to 0 0 0 XOR s. Okay, I hope it's clear. Now only one question is left though. How do we do this transition? Okay, how do we make this transition? Well, maybe you can see that we're applying some sort of a controlled operation here, right? When this index is 0, we do nothing. When this index is 1, we do something. Okay, so obviously this is a control operation where the control qubit is first registers, this guy's third index. Okay, now how do we do this XOR thing though? Okay, how do we do this XOR operation? Okay, let's notice. For example, when you take 001 and XOR with 101, what happens is basically you're hitting this state with X gates where S has ones. Okay, you hit first and third index with X gates, you turn it into 100, right? For example, for 011, you hit a X gate here, you make it 1. You do nothing here, it stays the same. You hit an X gate here, you make it 0, right? So you actually, what you do is you apply controlled NOT operations to make this transition, where the control qubit is this index. I will name it as least index in the code, and the target qubits of the second register are going to be the ones at which S has ones, right? So that's how you're going to make this transition. So let me go over the code, maybe it will make it more clear, but if you have any questions, like it's not something to understand very easily, I have to do a lot of work myself. If you have any questions, you can just email me. Okay, so first we just like our Simon Oracle function just generates a random string. Okay, it just literally flips a coin and adds 1 or 0. Okay, now after having this like bit string S, what do? We just initialize a quantum circuit, right, with 2 times n qubits. Like the first half is for the first register, the second half is for the second register. Okay, now what we do this copying operation from like right here from x0 to xx. And how do we do it? We apply CNOTs between ith and n plus ith qubits. Okay, now after applying this CNOT operations, basically we have achieved this state. Now remember, what do we need to do this state? We first need to know how many ones are there in S, right? Because that's how many CNOT gates we're going to apply. And also we need to know what's this index E, like I, that I was talking about. Okay, what's our choice? So we go over this S string, okay, and for each one that we observe, we append it to the set of indices list. Okay, this contains the indices at which S is equal to 1, Si is equal to 1. Okay, And we also need like this least significant index, least significant being the rightmost, at which Si is Y. So we get it by the last index of this set of indices. Okay, I also have this like least significant index. Now, what do we need to do? We need to apply CNOT operations, all right, for each one, all right, where the control qubit is least significant index of the first register, and the target qubit is the ones at which there is a 1. Okay, well, we have the indices at which there is a 1 in S. Okay, so we make a loop over it for each target in this set of indices. Okay, we apply a CNOT. And the control operation, like I said earlier, is the least significant index, and this is like, this corresponds to second index. Okay, like the first n of them are the first register's index, and the second half is the second register. So we add an n to reach those points. Okay, now just what we're left with is just make this transition. We just make some X gates to all of these indices to apply this non-trivial, let's say, mapping, and we're done, right? We just transform this custom circuit that we have made into a gate, and we append it into our quantum circuit, and we also return our string. Okay, this is, well, for me it was very hard to grasp, but I'm sure it will be way more easier for you. So I highly suggest that you just like go over these calculations and actually see that they work. Okay, you can just refer to the table here for different S values, okay, and see that it actually works. I also like, there's also a nice thing that you can do. At the end, remember I added some X gates. Well, the question is, what else can you add? Like, you don't have to apply X gates, right? You can just apply some other gate and probably get some other mapping. Now, the question is, what's the condition? Like, what kind of gates can you apply so that this becomes a valid, like you don't lose this fx property that you have? Okay. Also, again, if you want to know more about the subject, I suggest you take a look at Simon's algorithm in Qiskit textbook. Although they don't, like, what we've covered here is actually the chapter problem, but anyways. So, and in the in the last cell, you can find the definition for Simon solver, which is a very inefficient linear system solver that I've defined. Well, thanks a lot for listening and participating.